Continuing in class 21, here's example 6.5. We want to calculate the change in entropy per kilogram as air is heated from 300 degrees to 600 degrees Kelvin, while the pressure drops from 400 to 300 kilopascals. Assume constant specific heat, and then also try it with variable specific heat, and we're going to stick with the method that we might refer to as the standard entropy method, where we look up the standard entropy. So let's tackle this daunting task. To start with, let's look up some variables. Okay, so we're not going to use this anymore, and we're not using that, right? So let's go to our gas constants, and we're going to use air this time. We've probably looked it up a bunch of times, and we maybe we're even memorizing it at this point, but let's look it up anyway. So write this down, that the gas constant 0.287 for the ideal gas law is this, and then we're going to have, I think we're going to use the CP for this, so we're going to 1.004, and we'll come back to this one when we need to. Kilojoules per kilogram degree Kelvin. So recall that I have it written up above, but I guess I'll write it up here. T1 is 300 degrees Kelvin, where P1 is 400 kilopascals, and T2 is 600 degrees Kelvin, and P2 is 300 kilopascals. It's supposed to be an A. Looks like a 2. And then I looked up those values right there. Okay, so we looked up those values. Let's get the delta S is going to be CP natural log of T2 over T1 minus R ln P2 over P1. Definitely the easier approach, but let's see how well we do compared to the other table again. 1.004 natural log of 600 over 300 minus 0.287 natural log of 300 over 400, and so we'll get a delta S. Slide the paper up. Where are you at? 0.7785, and these are kilojoules per kilogram degree Kelvin. So I have to decide, let's see, is this a good enough approximation? Let's try it with the variable specific heat. So we will take a look, and this is air, I believe, so let's take a look at which table we need to use for this. And we see, okay, well, right away, this guy right here, this is our table, A71, and we had 300 degrees Kelvin, and we're going up to 600 degrees. So the one that we want to use is this for 300, and this for 600. So let me write that down. This is table A71. And T1 is 300 degrees Kelvin, so ST10 is 6.86926. I'm not sure we need all of those sig figs, but I wrote them down anyway. Dropping sig figs is just going to make the number at the end not as reliable, but not necessarily accurate 100%, but because there's an approximation going on inherently, but it's not going to help it any. So the delta S through this, I keep forgetting the name, whatever it is, the standard entropy method, going to be equal to ST2 minus ST1 minus R ln P2 over P1. And truth be told, I never remember ever doing this before in my life. That's okay. It's interesting how it works. So we'll go 7.57638 minus 6.86926 minus 0.287 natural log of 300 over 400. And what we'll end up getting is, where'd you go? 0.7897 kilojoules per kilogram degree Kelvin. And you can take a look at the difference between there yourself a little bit. This is more. So this is, so I might write out a sentence when I go to compare. Because I think that, you know, to find two things is that's well and good, but how much different is it? Well, we should look at the percentage difference. CP, or constant CP results in I want percent difference equation here, right? Go to absolute value of 1 minus the one that you're comparing. So I'm going to compare to this. So I'm going to compare this to that. So the one that you're comparing, 0.7785. And here's the base that you're comparing it to, 0.7897, is going to have 1.42% less than standard entropy, STD entropy method. Right there. So now we know what our comparison is of these two things. We're only 7 minutes into this. Let's go ahead and do another video, even though I get tired of uploading them. This is way too many examples, but I'll continue with this. All right, so another video. Tired. It's 10:49 at night on a Monday.